Thanks very much, Tama. Thanks for this kind introduction, and thanks for inviting me to speak. Thanks also, Peter, for initiating and allowing me to spend some of my sabbatical year at this illustrious institution. So the title of my talk was just read by Tamar. This is a joint work with Steve Lester, who is my colleague at King's College London. And I'm not going to say anything which is not joint. Okay, so as it is obvious from the title of my talk, the main subject is the Gauss circle problem. So let me introduce something. I'm sure that everybody knows it, but part one is motivation. The Gauss circle problem and heuristics conjecture. Okay, so let's introduce the following notation. M of R is by definition a number of lattice points lying in a circle of radius capital R. R is going to be a very large parameter. I think that Peter doesn't agree with this notation. I think that Peter thinks that there should be R and not R squared, but I'm going to use my right as a speaker to decide on notation. And I think that some people want for this one. So first, let's determine the asymptotics of this number as it was done by Gauss in 1837. Okay, so let's consider this picture. So around every lattice point, we draw a small square of side length 1. And we are going to count in all the squares that are going to be centered at lattice points inside the disk, and count out the squares that are out. Okay, so whatever we have is some kind of polygonal shape. And just it is easy to convince you that because the diagonal of the circle, the diagonal of the square is square root of 2, that this polygonal shape, it might get out, but it lies, it contains a slightly smaller disk, and it lies entirely inside a slightly bigger disk. So we can write that n of r is smaller or equal than pi of r plus square root of 2 squared, and greater or equal than pi of r minus square root of 2 squared. In fact, we can even divide it by 2, because what matters here is the half diagonal. And that already implies that n of r is the area of the disk plus big O of r. So this is the main term, this is the error term. And the error term is proportional here to the circle length. This is a take-home message. Now, let's subtract the main term and see what kind of error term we get. So we take capital delta of r is by the definition n of r minus pi r squared, which is by Gauss is big O of r. But in fact, it was proven to be is big O of r to 2/3. This is independently by Sierpinski, 1908. Van der Korput, 1920, and Vorman around the same time. Okay, and the Gauss circle problem, okay, this is not the optimum. The Gauss circle problem is to determine the optimal exponent in this upper bound. So alpha naught, which is the infimum of alpha, so that delta of R is big O of R to the power alpha. So up until quite recently, the world record belonged to Huxley, which is this number, and you can see how much progress we did in whatever number of years since Sierpinski et al. And Borgen and Watt a few years ago improved Huxley's bound to this number. So this is the present world record. Now, conversely, there are lower bounds. So Hardy in 1915 proved that delta of R is not big O of R1/2 log R1/4, meaning that there is a sequence of R so that the ratio between these converges to infinity. And he did it, in fact, for both plus and minus with different powers of log. And he conjectured that alpha naught equals to precisely 1/2. So since Huxley, this lower bound was refined for rare sequences by Hafner and Sound that improved and beat this result by some powers of logs.
You say, I forget why the plus and minus are different.
The plus and minus are different, yes.
Can you remind me why? Do you have to line up frequencies? It's easier to line them up in one direction than the other. You know?
I don't remember. I'm sorry.
Hardy actually made a mistake. I think he first claimed that the plus and minus were about the same, and then he had to start to realize that it's actually more so. By the way, this lower bound is true for geometric reasons. It's got to do with the fact that if you have any manifold, and this is the count, so like a torus, the fact that there are bouncing ball geodesics all of the same length, a one parameter family of geodesics on a torus of the same length, you can get the same lower bound. So that R, but I can't remember whether it's plus or minus. It's in the old.
I don't remember it either.
It's in my sure lectures. I explain. So you can explain it just from semi-classic.
I take it as
the lower bound. Yeah. So it's never, because it's not obvious that it's not smaller than R to the half.
But yeah, you argue that it is obvious. It is.
I'm saying that Hardy's proof is kind of subtle.
It's subtle.
Yeah. I mean, you got to produce some poll somewhere of somebody. He doesn't. Yeah. You're not talking about the lower bound.
No, I'm not even talking about the upper bound.
Okay.
When did Hardy prove his stuff?
1915. 1915.
15.
More than 100 years ago. So now, why should we believe the alpha naught equals to 1/2? Why is this exponent? So if we are looking at this proof again, then those squares that are far away from the boundary are going to be fully contained in the disk. Those squares that are far away from the boundary from the other side are going to contribute nothing. So really it's about those squares that are somewhere on the verge of the boundary. For example, squares like that. And the contribution of those squares, we can model it as a Bernoulli variable, random variable with probability 1/2. So we have around R squares of this type, because this is proportional to the boundary. And we model it by binomial random variables, so by the usual laws of random numbers, large numbers, if you want, or central limit theorem, almost surely it's going to be the fluctuations are going to be of order of magnitude squared of r. This is the folklore heuristics, why it is 1/2. So. Of boundary. I made a mistake. As IID Bernoulli on variables, and there is about some constant times r fluctuations about. This is the heuristic explanation, and we're going to try to make this heuristic explanation a little bit rigorous and prove some theorems with that. Of course, it cannot possibly be true literally for two different reasons. Suppose that we model the contribution of those squares as ID random variables that are Bernoulli. So first of all, if this is indeed true, then we would have gotten square root of r clean, and it would be too strong to be consistent with the lower bounds. And second reason, let's suppose that I know that I have a lattice point, say here. And of course, it will have some impact on the lattice points nearby. So it cannot possibly, two nearby lattice points are not going to be independent in any kind of sense. So it can't be literally true. So we're going to introduce the following quantity. Fine. So, okay, so what are the lattice points, or what are the squares that are around the boundary? So it's quite obvious from the picture that we need to take all those lattice points lambda that are bounded in this angular area between r minus 1 over square root of 2 and r plus 1 over square root of 2, because half of the diagonal of the square is 1 over square root of 2. So for lambda like that, lambda between r plus 1 over square root of 2 and r minus 1 over square root of 2, we're going to define the following notion. A r of lambda is going to be, so this is the lattice point. This is the square. We're going to take a square centered at this point, and we are going to count the area which is contained inside the intermediate circle of B of R, which is the disk, section with S, which is the square, translated by lambda. And we are going to also use the notation S of lambda, notation S plus lambda. And we are going to use these two notations. Gamma R is going to denote those lattice points that we're interested in. And K of R is going to be their number. We're going to use this whole lecture, these two notations. Okay, now we have the following connection between this particular quantity, AR of lambda, and the Gauss circle problem. So we call it the connection formula. N of R minus 1 over square root of 2 equals to it's the other way around. pi squared equals to n of r minus 1 over square root of 2 plus sigma lambda belongs to gamma r of a r of lambda. Why is that? So this is basically what we discussed here. What we did, so we have taken, so this is the area, so pi r squared is the area of this intermediate circle. We took all the squares that are centered at points lying in the inner circle. They're all fully contained inside this intermediate circle. And we add all the parts of the squares that we missed in the first summation. So this is the connection formula. I'm never going to use this formula. This is just to relate between this quantity AR and the Gauss circle problem directly. There are some other connections that we have in the paper. And now let me state the main results. Any questions so far about notation? So. So our results concern the distribution and various finer properties of these numbers AR of lambda as lambda varies in gamma r. And these are connected to the Gauss circle problem. In particular, one of the main questions is how to formulate this independence principle. Now we know that there is no independence here for the two reasons that we mentioned, but maybe if we have two far apart lattice points, maybe there is some independence, and we will be able to explore this idea, and we're going to formulate it via these numbers. And I'm going to warn in advance, we're not going to improve any of those great exponents of Bourgain and Watt or of Huxley, but this is a second order results that what I am going to present, not first order results. So first of all, expectation. Expectation of these numbers is really easy. So what is, by definition, the expectation is 1 over k of r, summation of a r of lambda, lambda in gamma r. And I'm not going to state it as a theorem. This is 1/2 plus big O of r to minus 1 over 3. This is just a restatement of the fact that alpha naught square is less or equal than 2 over 3. I'm sorry, I'll have to change the natural order of this board. Okay, so theorem 1 concerns the variance and the limit distribution of these numbers. So the variance, V of r, which by the definition is 1 over k of r sigma AR of lambda minus the expectation, which is by 1/2 that we just discussed. And this is C naught plus little of 1.
It's not square.
Square, all right. Thank you very much. That's important.
The only thing I know is what a variance.
So this is C naught. And C naught is this number, which is very explicit. And importantly, it's positive. Okay, and number 2 is that these numbers AR of lambda converge in distribution as a random variable to some random variable, which we call infinity. which is a random variable supported on -1, 1. And okay, in particular, this random variable has the clean variance being C naught. Okay, so from 2, statement 1 follows immediately because we're dealing here with bounded random variables. So we have a convergence in distribution of bounded random variables. Then we also have convergence of all the moments. So 2 is stronger than 1. Now we're asking the question how to formulate the independence of those numbers. For this purpose, we're going to order this AR or this lambda according to non-decreasing order of their argument. So write lambda j is lambda j times e I theta j. Right, theta j. This is just the polar coordinates. And order this according to index j, according to non-decreasing order of theta j in a circle way.
Does this have to do much with the circle? I mean, you could just take any curve in the plane.
Yes.
And ask how many integer points are underneath it. Say it's convex. I mean, firstly, the whole problem's local, right?
Yes.
It's not a global, and the circle could be any ellipse and could be any convex. So then you have to do this locally.
You could do that, yes.
Because the feature of the...
Well, actually, we will have some global results as well. Yeah. So, yeah.
I'm just trying to understand what you're trying to do. You're modeling this as a random variable, gives the wrong answer. You want to now try to understand better why it's giving the wrong answer.
Not
Trying to
right.
recover the fact that the variance, the remainder term is not really not random. So what is it you're trying to do?
I will
Okay.
formulate the result, and maybe it will become clearer. So with order according.
The two-thirds true if you replace the circle with the convex curve of area r squared. And
Yes.
Yeah. But that uses Poisson's sum.
But what we're trying to do is to formulate this folklore heuristics that states that that we can model these points, whether or not they're inside or outside, as independent random variable. You'll see what I mean. So we order according to the non-decreasing or increasing theta j. Okay, and now we have the following result.
Stationary page.
Okay, let's take that A is some number greater than 1. This is going to be the correlation distance, and we're going to sum A r of lambda j, A r of lambda j plus k. Okay, this is the correlation. J goes from 1 to k of r. This is, by the way, this is little k, and this is capital K of r. This is not the same thing. Okay, so in order to make it into a correlation, we subtract the product of the expectations. So this is 1/4. Okay, and take lim r to the fifth. Okay, so we have the following result, that for every k, this limit exists. Let's call it curly CK. So theorem for every k, CK exists as a limit. Okay, and the conjecture is the following. That the limit as k goes to infinity of CK vanishes. So this is, if you want, this is the formulation of the independence principle, which stands behind the folklore conjecture. Any questions about it? Okay. So as far as I know, this conjecture is at this point open, as stated, but I have some results to support it. And this CK are some absolute numbers. We did some numerics. So I'm going to state several results in support of this conjecture. So first, numerics. And the numerics were consistent to CK, some oscillatory function of k divided by square root of k, or give or take square root of k. So the numerics are consistent to this conjecture. And moreover, there is some vanishing rate, some decay rate too. I think that if somebody wants to run better numerics, and maybe somebody feels more qualified than we do, I think this is an important question to resolve. Now I have the following theorem. This is theorem 3, so this is theorem 2. These numbers CK vanish on average. Meaning that sigma 1 over L, k goes from 1 to L CK vanishes. Okay, so this is a rigorous support to this conjecture, number 1. Number 2, the following result. So instead of ordering these lattice points by increasing theta, what we do is we actually look where this theta falls, what interval it falls into. So we are going to consider a similar sum. They are lambda minus 1/2. They are mu minus 1/2 over tuples lambda mu lambda r, so that the corresponding angle lies in an interval of size 1 over k, essentially k over k of r and k plus 2 pi divided by k of r. Now, we divide by 1 over k of r. Given a lambda, we expect for precisely 1 mu that would lie in this distance in terms of angle, because the number of angles is k. So we expect the next one to be in distance 1 over k in terms of angle. Okay, so therefore, this sum, if we could justify, if it would be only true that if such a rigidity would hold, then that would be already the resolution of this conjecture. But this is not true, and this is not expected, and But nevertheless, so and sometimes there will be 0 lattice points in this interval, and sometimes there will be more than 1, up to some bounded number. But nevertheless, so lim r tends to infinity. Okay, any questions? Okay, we have more results to support. But instead of that, let me give some details, some ingredients of the proofs, what we actually are doing, unless there are some questions. Okay, so part 3, run the models. Okay, so let's suppose that we're given a lattice point in gamma r. We're going to use, instead of the polar coordinates, we're going to use the shifted, what we call the shifted polar coordinates. So lambda equals to r plus r lambda e I theta lambda. Okay, what is the advantage of shifting the this coordinate? Is that r lambda is between -1 over square root of 2 and 1 over square root of 2. No matter what capital R is. And theta is always asymptotal, it is 0 to pi. And we have the following fact. Let's consider all the tuples r lambda and theta lambda as lambda varies inside gamma r. Okay, so these are some tuples inside the Cartesian product of these two intervals. By the definition, this is -1 over square root of 2, 1 over square root of 2. Cartesian product is 0 to pi. So the fact states that these tuples equidistribute in this rectangle. But this is not terribly difficult. We can do by Poisson summation formula. Now let's try to magnify the picture.
These results also extend to Z3 or higher dimension?
We did not consider that, but I think it's this is one of the things to do. I mean, I don't see an obstacle.
Of course, the problem becomes trivial in 4 dimensions because the number of lattice points inside these regions, because the lattice points are so degenerate, the remainder term is as big as the jump. The lattice point problem for the standard lattice, if you take a random lattice, it's very hard. But if you take the standard lattice in dimension 4, it trivializes, meaning the jump, the remainder is as big as the jump. On how many ways you can write a number as the sum of 4 squares is so big. So it becomes boring from the maximum size. 3 is still hard. I don't know who's got the world record on that. Maybe Ivanets and Chimizo or somebody.
Okay, so let's magnify this picture. Well, let's magnify the relevant part of this picture.
I mean, you're really studying lattice points in an annulus of area, not 1, but area square root.
Of area R in this notation, yes. This makes it
Modeling on this, if it's area 1, where you're supposed to get a Poisson process, as you know, then the circle is false and ellipse might be true. So that's how tricky that gets. That's the problem that Dyson and there's local spacing between the eigenvalues of a torus, which is not the square torus, but a 1√2. Yeah. And it's much harder.
Right. So let's take a typical lattice point. Let's say it's here, and draw the square around it. So this is going to be lambda j. Now let's shift this picture by lambda j, so that we put lambda j at the origin. And what we notice is that in fact this picture is a little bit misleading, because since R is so big and the square is of size length 1, locally this is almost all of these three are almost like straight lines. So we can approximate by straight lines. So let me translate that. We have a square and we have some kind of line like that, and we're interested in this area. Now this is becoming the origin. And we're going to make one more transformation. We're going to rotate the square so that to make this line vertical. And moreover, we're going to shift it to the right, in this case, so that this is going to become the y-axis. So what it becomes is the following. So this is becoming y-axis. Now the square itself is going to be rotated. And this is going to be this bit. And so where is going to be our point? Our point is going to be distance r, and r is the same as the r lambda here. So this is going to be, so what I'm trying to say is that what we did to this square is we rotated it by theta, or maybe pi over 2 minus theta, and shifted it by r. And whatever is modeling AR is this bit, which is to the left of the y-axis. Okay, so what we did is the following. Let's define the following random variable, a infinity of r theta. Okay, so we take the square. That's like 1/2, 1/2. Rotate by theta. Shift by r. And the resulting random variable a infinity is whatever is remaining to the left of the y-axis. Okay, so if we take r and theta to be equidistributed wherever it's supposed to be equidistributed, that is in G, then this is a random variable, and not just a function of r and theta. And it is possible to write it completely explicitly as a function of r and theta. And we have to divide it into 5 different ranges. So I think that this I would like to retain. I started. So as r theta are uniform in G, A infinity is a random variable. And what we actually proved is the following. And whatever picture we just discussed is actually possible to make it into a proof. It's not entirely trivial. Is that AR of lambda, where lambda is in gamma R, converges in distribution to A infinity. In order to, we've made two statements about the distribution, which is this A infinity, the same one, and we also claim the variance. So there are two ways to compute the variance. One is an ad hoc proof. The other one is to write A infinity explicitly as a function of R and theta. We had to divide into 5 different ranges and compute the resulting integral. And this is the number that we got. And both ways we got the same number, which is why we're quite confident that we got the correct answer. This number is not something universal. Now, I would like to upgrade the independence conjecture. If you remember, the independence conjecture stated, where was the conjecture? Where is it?
So the right
There, you look at
top,
Yeah.
right,
Top right.
top right.
Top right. Ah, yes, right. So in fact, we also have a convergence version for that. Now, what would be the natural conjecture, given that what we know, that if we take, so refinement. So we consider AR of lambda j and AR of lambda j plus k. We take the double limit. First, R goes to infinity, and then k goes to infinity. The question is, what would be the natural limit? So one thing, one notion that we got is supposed to converge to two independent copies of A infinity, because we know that all the marginals converge to A infinity. But in fact, this is not true. And from our results, it's possible to conclude that. But the refined conjecture is the following: that it converges to y1 and y2, and y1, y2 is A infinity of R and theta, and A infinity of R prime and the same theta, where R theta and R prime are uniform in G times minus 1 over square root of 2, 1 over square root of 2. In other words, R and R theta and R prime are independent, but the theta is the same. And the reason that it happens is that because we first took the limit R to infinity, and only then k to infinity, what happened is we constrained and we biased the lattice point, so the corresponding angle is the same. So therefore, this is not really a surprise. But this result is much more reasonable. And in fact, we prove this result on average. In fact, y1 and y2 are not independent. But uncorrelated. It is possible to prove that if we are looking at AR lambda j plus k, then for every k, this has a limit distribution. Then in the double limit, it will converge or not converge to this random variable. But we can prove it on average. And this result certainly implies the theorem 3 that CK converges to 0 on average. Now, I think I have sufficient time to explain the random model and so theorem 2, why the random model for the correlations, right? So okay, so let's suppose that K is given. And let's magnify again the picture. Let's suppose that we're in the first quadrant. Let's suppose that we have some lambda j. And we're supposed to compare lambda j with lambda j plus k. So then we have lambda j plus 1, etc. Until we have lambda j plus k. Now this picture is again a little bit misleading because really R is very large. So this area looks very much like a rectangle. Okay, so this is lambda j. So what we do is we are going to really think about it as a rectangle, and we are going to translate it to the origin. That is, we are going to translate this rectangle, or approximately rectangle, by lambda j. Okay, so maybe I'll So what happens after we translate this rectangle by lambda j? So what we'll have is a rectangle like that of side length square root of 2. And this is a semi-infinite rectangle. Here, this is the origin, and this is what used to be lambda j in the before the translation. And then what we're going to look for is lattice points inside this rectangle. Now, Z2 has the property that this is invariant with respect to integer translations. Therefore, whatever lattice points we're going to find here, we can translate them back and get the lattice points inside the disk. So if this models lambda j, what would be the model for lambda j plus k? So what we're going to do, we're going to look at this rectangle. We're going to look at the lattice points on the rectangle. And we're going to order them according to the projection to the long side. So this is lambda j plus 1. Sorry, this is lambda j plus 1. This is lambda j plus 2, etc. And this is going to be lambda j plus k. So what we are going, and what is going to be the corresponding AR? So AR is going to be, we're going to divide this rectangle into 2 halves. We're going to take a square like that, and this is AR. This is what was AR. So let me just summarize. What we did, we took a rectangle. We rotated it by a random angle. So that it becomes something like that. But we also need to shift it by distance r in the direction of the short side, because this is the origin, this is the new origin that corresponds to the point lambda j with shifted polar coordinates r. And r has to be random. Okay, and then we're looking for, so this is the origin. Then we're looking for lattice points, and whatever the kth lattice point we find, this is going to be our lattice point. And whatever part it has in this half, this is going to be the new random variable. A infinity point k r and theta. Are there any questions? And then what we proved. Okay, now we have two random variables. One is a infinity of r and theta. They're defined on the same space. And I claim that ck that appears in theorem 2 that was already raised, but this is the claim the existence. This is precisely the covariance between a infinity and a infinity. The vanishing of on average of ck amounts to the following interesting fact. So if we take theta generic, and we're going to look, okay, so we have a rectangle like that. So we're looking at lattice points. So it turned out that the projection on the short side of those lattice points equidistributes in this short side. This is, of course, not true for every angle. If you take this angle, that is a horizontal rectangle that does not, that we do not rotate, then we have all the lattice points are going to be on the x-axis. Let's suppose that we don't shift it. So the corresponding distribution of the projections onto the short side is just the delta measure at the origin. But it is true if we stay away from angles that are close to rational after taking the tangents, then they equidistribute generic angle. Let me make two comments about the proof. There are two obstacles here, and both of them are non-trivial. So two bad things could happen. First of all, there is a discrepancy between the rectangle and the circular arc. And we might get one point which belongs to one of them, but not to the other. Then it screws completely the business because the order is going to change, even if it's not the correct K. And second, even if the lattice points between the rectangle and this sector are the same, the ordering might be different because one of them will order according to the argument and one is according to the projection side. As part of our proof, we prove that both these are rare, but could happen. Okay, I think I'm not going to write it. So I think I'm finished. If there are any questions.
Yeah, since this is a special year seminar, let's bring in some ergodic theory. So, question one. This Erdos people will answer me. Erdos has some theorem about if you have a sum set, which is looking at x squared plus n squared plus m squared. And you count how many integers there are in the sum set in some ranges. He gives a lower bound of square root. I'm trying to understand the lower bound. You don't know how to prove the lower bound from your point of view rigorously, because that's supposed to come from general principle, that lower bound. So firstly, what's Erdos theorem? Nobody knows.
I know one theorem about you have a set of integers a, and a plus a contains the first n squares, then a must have size at least n to the 2/3, and to the 1/2 is trivial, but doesn't seem relevant to the Hardy lower bound.
I think. Yeah, so the issue I'm trying to understand is the lower bound. So if you suppose you did the same thing, but not a circle, but a triangle. So people have studied the number of integer points in a triangle. Hardy and Littlewood too. Of course, the angle must be irrational. Then you can give a lower bound, and it's the kind of sum you're writing down a fractional part of. You can always convert it to a fractional part, which is the way I would. I mean, everything you're doing, I believe, should be a general thing that if you have a curve f of x and you count the number of integer points under the curve, that's what you're doing, and you don't have to be a circle. Because you're not really using it as a circle, you're using just the tangent there and you're approximating it as a circle. So then it's the fraction, the number of integer points under a curve will be the fractional part. That'll be your variable, the number minus a half expected values you average over. And you'll get the same 2/3, by the way, that way. Upper bound. But the lower bound should be, I think, much more general. So if you are however, if you are a straight line, if you're a triangle, then you've curvature, and then giving a lower bound is very difficult. It was done by Veroshosh. The conjecture of lower bound of fractional parts of n alpha minus a half. That lower bound. And the Manchik just a few weeks ago gave me a lower bound using cocycles, using ergodic theory, reproving a theorem that you cannot be bounded. So there must be some discrepancy. So there, of course, it's not square root when you straight line for any alpha which is irrational. So my feeling is that the lower bound is supposed to be something very conceptual and come from many different points of view. I can give you a Fourier. The Hardy's lower bound is not trivial. I've seen people conjecture that it's smaller. And the one way you can do it, I'll show you using micro-local analysis in a second, but when we finish. But I'm just trying to understand why you're not seeing the lower bound from your method. The upper bound, so you should have a model whereby it's kind of obvious that the lower bounds are to the half.
So we do get some non-trivial upper bound from our method. We did not try to.
So you're not going to improve the upper bound by your kind of analysis unless you go into the standard tools which are involved in what Watt and Bergen are doing and Huxley before. Unless you have a new idea, but the lower bound should be a conceptual thing. That's all I'm trying to say.
I understand.
You
We
model
will
it.
try to optimize it.
Yeah.
But you don't care whether they're flat pieces or not?
So you should be using somewhere that it's everywhere positively curved.
Yeah, that's what,
That must be an input.
that has to be there.
One thing that will
But if you flat an irrational angle, then the lower bound is very hard, and just the fact that it's unbounded is a very deep fact. This is a theorem of Veroshosh.
one thing that does depend on the circle is this statement. So for some other curve, it's going to be a different distribution.
But your analysis will work the same way.
I agree, yes.
So, I mean, your analysis is local. Your 5 pieces is different coordinates to. Yeah, in other words, you're writing square root of 1 minus x squared. You're keeping away from. You're writing a good chart so as to do the analysis under a curve. Yeah, I believe. So I think in the book of Linnick and Gelfond, it's called Elementary Methods in Analytic Nomenclature. Beautiful book. They discuss this problem, and I think they give the Sierpinski theorem for under any curve, not the Poisson sum proof. That's one I know.
Is there a convex curve for which the R of the 2/3 is sharp. So in the style of Bombieri-Pilat. So
No, so then no, you have to, no, if it's strictly convex, no, all of Huxley goes for strictly convex.
yeah, but upper bound, is there a better construction than the Hardy one for some other curve? Is there some curve for which
I don't know.
the error term has to be larger than maybe
I think if you smooth analytic, we expect this the upper bound to be the same, R to the half plus epsilon. I don't think so.
There
If
is,
you make your curve have some singularity, I mean, of course, you can make,
there is also Vinogradov's treatment that is valid for any curve.
so what's Vinogradov saying?
2/3.
Yeah, so that's done in this book. Yeah, so, right.
Can
For
I,
any analytic curve, what's the condition? Smooth?
C2 or C3
Yeah, but it
and,
mustn't be a straight line.
and like some curvature.
Yeah, that's,
the conditions to say C3 for technical reasons?
I mean, depending what you call technical, I mean, it's difficult to do differential analysis.
You much more general question. Whatever you do, what the possible applications it gives.
that's below, you're hitting below the belt.
No, but I don't mind going to that.
It's a problem in analysis. It's a problem in analysis. Because when you're counting in a Diophantine world, you can always smooth. But you're not normally counting short. This is about how many points there are in a circle, an exact circle cut off.
But Gauss was interested in sums of two squares. So that was why Gauss.
I think they were trying to approximate the area. There's some beautiful lectures of Huxley on the history of this problem, but going back to Gauss.
So that's exactly what I wanted to understand. So it's not obvious that Gauss has something Diophantine in mind, right? No, I see.
It's not obvious.
I mean, it is the number of integers in the Gaussian integers of norm less than x.
It is a second order result. It's not whatever I presented is not a first order result. So first order result has to do only with the expectation of these numbers they are, but we go beyond the first order result. So we do not improve any first order results if you want.
And then maybe Peter or you, Igor, know what was the methodology of Poin, what relatively to Huxley? It was Fourier analysis?
The most important breakthrough is Bombieri-Ivanets. They got, they're 2/3 or 1/3, I don't know anymore where. Anyway, that Sopinski result is just Poisson's sum of dualizing. Proving that is called an alpha-beta process. You do it, you apply Poisson's sum twice, but you intervene with the operation and repeat it. And that goes slightly below 1/3. And Ivanich and Bombieri wrote a paper which sort of changed that to something a little more reasonable. So they went quite a bit below 1/3. I mean, these numbers, like all world records, if they're not improved over a long time, they start to look like big gains. Bergen and Watt are improving. So Huxley is following Ivanich. So Huxley has a book. It's basically saying I'm exposing the method of Ivanich and Bombieri. And Watt, I think, is a student of Huxley probably. And Bergen uses this decoupling in some part of the analysis to improve just one piece somewhere and otherwise using the whole machine. Not sure the Bergen Watt paper appeared, did it? I think I was dealing with it. Nobody except Bergen understands it. Understood it. Nobody could verify it.
Nowadays, if nobody except Bergen understands them.
That's the problem there. I think, well, I think, yeah, I'm not sure it's that paper. Where is it published?
I mean, it is on archive.
Yeah.
Whether it was accepted to a journal, I don't know. I mean, I haven't seen it being accepted to a journal.
Yeah. Okay.
More questions?
Just regard, what about we replace this square planetary by other planetary,
But what?
tiring
Okay, yes.
common sport?
That's a good question. We can do that. It will change probably. So, I mean, it will change various tools intermediate, but like the end result will be the same, essentially. You'll get like different distributions. But I think that, so for this specific problem, I think that the squares is the most natural choice and most obvious. But it becomes important actually. So, and I think that this is a good problem for a PhD student, what to do with, as you say, either different tiles or different lattices, which is equivalent models. I mean, you're going to get a different distribution.
Okay.